Hey, there's an interesting function here that I would hardly have any idea about in terms of what it really looks like that we're trying to determine the maximum value of. The function is x raised to its reciprocal, and it's x raised to the 1 over x, to be more specific. Now, we're going to only focus on the positive real numbers. Notice that 0 is not even in the domain of this function. You'd have 0 raised to the 1 over 0, which is undefined. Now, that is an indeterminate form, but arithmetically, it's not even defined at 0. So 0 is not in the domain of this function. Now, we're interested in finding the maximum value of this expression because it ends up helping us to compare some interesting exponential expressions in terms of their magnitude. So now the method employed here is logarithmic differentiation. We start out by taking the natural log of both sides. Now the reason why we do that is it's easy to differentiate the natural log function. Now notice how I did skip a step here. One of the properties of the natural log says the 1 over x comes out to the front. And I did that. I could have shown 2 steps right here. So this is kind of some algebraic manipulation going on. And now we differentiate both sides of this expression. We differentiate this. The derivative of the natural log of y is y prime over y. And then right here, this can be written as ln x over x. This becomes a quotient rule from calculus. All right, and this is a special rule here that says it's the bottom function times the derivative of the top function, which you see right here, minus the derivative of the bottom function times the top function, which you see right here, over the bottom function squared. It's just a rule from calculus. Won't go to the trouble to try to prove that. I don't know if I could. But anyway, this is referred to as the logarithmic differentiation process. Now notice that tells us that y prime is equal to all of this, okay? In other words, y prime over y, excuse me. We get to this point right here. Let me write this down. Let me really kind of see if I can manage to highlight. Good, good. Now, yeah, you see right here how we started y prime over y, and then we have this piece. So I just wrote that down here. Now, we're not done because we found y prime over y. So if we multiply by y here, which is x to the 1 over x, we get this expression for y prime. Now, notice that everything inside, the x squared is always positive. X to the 1 over x is certainly always positive. All right. So the only thing that's alive is really the numerator here. And so we, to find horizontal tangent lines, we set the entire expression. We set this entire expression equal to 0, but that's really equivalent to just setting this part right here equal to 0, okay? And that's helpful. So right down here, we do that, and we get a fairly straightforward equation. Ln x and e are inverses, and so we get x equals to e is the only solution. Now, that means, and also, does that correspond to a maximum or a minimum value? Well, what you can do is you can check this derivative at a number to the left of e, the critical value. E is what we call a critical value. All right, we can check a number at the left of e, which it would be 1. That's a simple enough number. E is about 2.7, right? Okay. Now, so we get a positive derivative if we put 1 in here, and that's not hard to see. If you put 1 right here, this is just 0. Everything else is positive, right? So y prime at 1 is positive. Now y prime at e squared, that's another nice choice. It's a number bigger than e. And if you put e squared in right here, you get ln of e squared, but ln of e squared is just 2. So you would get 1 minus 2, which is negative. That explains this minus right here, okay? All right, so this means that the function would be increasing all the way up until e, and then decreasing once you got past e. And so that means that e raised to the 1 over e is an absolute maximum, okay? And that's kind of the result. E raised to the 1 over e is the absolute maximum on this graph, whatever it really looks like, okay? Now, and also we can conclude that it's decreasing for the very same reasons. We can conclude that the graph is decreasing on e to infinity. You see, when we picked a number to the right of e, we got negative. All right, so that indicates that the graph would be decreasing from on the interval e to infinity. Now, this is kind of the whole reason we did the video. Now it helps us to do interesting things like compare these two exponentials. Notice right here that if we choose 21, okay, if we choose 21 right here, that 21 raised to the 1 over 21 is in this form right here, right? Okay, again, this form are these two guys right here for 21 and 22, right? But notice, because the graph is decreasing, that means that this term right here has to be larger than this term. It's decreasing. So as you move to the right, everything is getting smaller, right? So even though this is a higher base, it's a higher base, this is still the larger number. Now, the thing that really makes this work is you do this kind of this exponential trick, raise everything to the 21 times the 22, whatever that number is, we don't care. By laws of exponents, this 21 right here will cancel with this 21 right here, all right? And so this expression evaluates to this neat looking 21 raised to the 22nd power. And in a similar fashion, we raise this guy here to the very same power, and the 22's cancel. So we actually get that the smaller base is bigger than the larger base. And the trade-off is that you're raising it to the 22nd power right there versus the 21st power right there. Okay, y'all, I thought that was interesting. Now, another nice question this answers is this. This is in the very same form as x to the 1 over x. This is x to the 1 over x. This is x to the 1 over x for the famous transcendental numbers e and pi. All right, and so using a very similar trick, we get that e raised to the pi power is actually greater than pi raised to the e. And that's interesting because e is about 2.7 something, pi is about 3. Now you have something that's about 3 raised to the 2.7. It's pretty close, very, very close. E to the pi is just barely bigger than pi to the e. You don't really see that here. But on this one that we did over here, 21 raised to the 22nd is much greater than this, it turns out. It wouldn't look like it, you might not think, but this one is much greater. Whereas over here, e to the pi, it's kind of razor sharp. They're very, very close. If you want, I don't bother with the decimals. I don't want to do that. Pure mathematicians don't do that. Anyway, I hope you guys enjoyed.